Just on time to our next speaker, which is Bastian Eppler. Bastian is at the Frankfurt Institute of Advanced Studies, and he'll be talking about abrupt transitions of response patterns emerging from gradual changes of network connectivity. Stage is yours.
All right, thanks, Elenor. Hi, everyone. Today, I'm going to talk about abrupt transitions of response patterns. This work was done together with my supervisor, Matthias Kaschuber, and is heavily inspired by experiments done by Dominik Aschauer and Simon Runke. So, first, for a quick motivation, we see abrupt transitions in model network responses, as well as in experimental two-photon recordings. And an example of these recordings is here in the top right, where you can see that a certain stimulus evokes a very stable response during an imaging day, and sometimes even across days. But then at the next day, here at day 5, some completely different neurons are active. So we were wondering, how are these abrupt changes linked to changes in the underlying network? And to understand this, we want to look at the fixed point dynamics of a circuit model. And where here at time point t, a stimulus can fall into a well of the energy landscape or an attractor, and we were wondering what is happening. So is it that the attractor landscape is only shifting slightly, which can still lead to an abrupt change in a response, or is the energy landscape changing drastically, which of course also leads to an abrupt change? So to address this, we have a model of auditory cortex. It's very simple, and we can already with this simple model reproduce findings from mouse auditory cortex in a regime that is dominated by strong inhibition and strong recurrent connectivity. The model is just, we have some random input, we have a firing rate for each neuron, and each neuron is connected to each other. Now what we do is we add some synaptic drift. In this case, it's modeled via some diffusion model, but it doesn't really matter. It can be any synaptic drift. And what we see is, here are some example stimuli and responses that the model or the responses are pretty stable until, in this case, around time point 70, when they change abruptly. We looked at a fixed point of these of stimuli, and we can also see that these seem to be pretty stable from time 1 to 69, and then again from time 71 to 95, but there's a new fixed point emerging at this time point where we also see these abrupt changes. So we were now wondering, how can we understand these transitions? And is it this slight or subtle fixed point changes? So in this case, only the unstable fixed point between two potentials is moving, but it still makes the stimulus be remapped to another attractor? Or is it something different happening, like new attractors appearing? To investigate this, we looked at a fixed point displacement. That's the distance between fixed point at a time point t to fixed points at a time point t-1. And if we have subtle changes, the fixed point displacement is basically 0 or small values, while when you have drastic changes, we would see a spike in the fixed point displacement. And also that's what we basically see. So the fixed point displacement here for 10 different stimuli is changing very slowly. Sometimes there are spikes, but there's quite a lot of spikes appearing at this time point where we see this remodeling of the response. And this can especially be seen very nicely in the sum that is displayed in black at the bottom. We have another problem here in this plot now, because sometimes it seems like fixed points completely disappear. So we don't see fixed point displacement anymore. And we were wondering what is happening there. So we looked at a dynamical solution of the system. And we did this by running the simulation very long. And we find basically 3 different behaviors. One would be fast convergence. That means the system is already converged and we don't see any change in the response anymore. We see sometimes slow convergence, where the model is still converging even after a long time, or sometimes we see more complex dynamics, which could be, in this case, is a 2-cycle, it could be larger cycles, or it could even be chaotic. And what we see here is that, again, these transitions seem to occur at the same time point where we see these changes in the response. So to conclude, we have a generic firing model that can reproduce key characteristics of neural responses for strong connections and strong inhibition. We see abrupt transitions of response patterns as a result from gradual changes of network connectivity. And these transitions coincide with qualitative changes of the fixed point structure and the dynamical solution of network activity. This I want to thank my supervisor Matthias and collaborators Simon and Dominic, and you for your attention. Thanks.
Thank you very much, Bastian. We do have plenty of time for questions. Just a reminder, you can use the Q&A function, you can use the chat, or you could put your virtual hand up, and then I can see that in the attendees list and allow you to switch on your mic. Any questions for Bastian? Oh, yes. Yes, Douglas, you're...
Hi, I had just one quick question. If you could go back to your previous slide. Yeah, so the conclusions one, actually, like when you say that it can reproduce these characteristics from like this abrupt transitions, right? And in response patterns, how I wonder how it relates to synaptic plasticity in the context of learning. So like I know you mentioned here gradual changes of network connectivity. So are you thinking of like synaptic plasticity induced by learning or some other kinds of changes in the network connectivity?
It doesn't really matter for this sort of behavior, of network behavior. So we can add any synaptic drift, we can change synapses more directly. We typically always see that if you change the synapses slightly, it does that nothing is happening until at some point there is this abrupt transition. And actually we think that it could even be a mechanism that's underlying this sort of learning that we experiment or that we experience ourselves, that typically or quite often when we learn something, we learn and learn and learn. And at some point there's this transition where we understand something. And this could be an underlying mechanism for this. And it comes in a very, very simple model. So.
Yeah, so yeah, I was just curious because like there are some very like big, abrupt transitions as you call it here, in the response of some neurons after learning. So I was wondering if it could be connected, and I guess it could be. Thanks.
Thanks.
Thank you, Douglas and Bastian. There's another question. Manuel, I've allowed you to unmute yourself.
Hi, can you hear me?
Yes.
Yeah. So you mentioned learning, and I'm not sure what are these networks learning, and I would like to also ask whether you try different tasks, if they are learning any tasks. Sorry if I missed that information.
Okay, so far the networks are not learning at all. We just change them randomly. I think it would be basically the same behavior if they are learning. So as long as
there is a task, if there is a goal, probably the fixed points at some point they will be stable, completely stable, because there will be some pressure to maintain them because there is a performance to maintain, right?
Yeah, probably yes. There's a really nice work on this by Susilo, where they also came up with the method to find the fixed points that we were using. It's called opening the black box.
I know that. So for instance, you could apply this same approach to that and see if when the fixed points arise and how abrupt is That would be interesting, I guess.
Yeah, definitely.
Okay, thank you.
Thank you.
Thank you very much. Are there any further questions? Yeah, Sadra, go for it.
Thank you, Bastian. I was wondering about the time scale of this transition. Maybe I missed it, and which parameters define that? Because, for example, in visual cortex, the time scale of this transition was a big issue for a while.
Yeah, thanks a lot. It's a very good question. Actually, the time scale doesn't really matter. We find these transitions on any time scale. So at least any we looked at. We looked at very large time scales, of course, but also at very small. And we couldn't they always seem to be abrupt, which is yeah, quite fascinating.
Thank you.
Thank you. We do have another 5 minutes before Neuromatch kicks us out of the room.